Hello and welcome. I am Karen Fox and I'm here at NASA's Kennedy Space Center in Florida to talk about NASA's newest mission, Parker Solar Probe. This is a mission to touch the sun. We are going to be flying through a part of the solar atmosphere called the corona, which reaches millions of degrees in temperature. It is going to be experiencing radiation and heat temperatures that are brutal. But as we go through it, we are going to have our first ever close-up look at a star. This is a particularly auspicious day to be talking about this. Today is July 20th. This is the 49th anniversary of the first time a human stepped foot on the moon. NASA has continued exploring ever since, and here we are talking about going to the sun as well. We have a few speakers here. Today in the room, we are going to have Alex Young. He is a solar scientist from NASA's Goddard Space Flight Center in Greenbelt, Maryland. We have Nicky Fox, no relation, even though we have the same last name. Nicky Fox, Parker Solar Probe project scientist from the Johns Hopkins University Applied Physics Lab. We also have Betsy Congdon. She is also from the Applied Physics Lab, and she is the lead for the thermal protection shield. That is the heat shield. We have an example of it here. We're going to be doing a demonstration with that a little bit later. We will take questions after the speakers have gone. We will also be taking questions from the phone, and we will be taking questions via social media. You can use the hashtag AskNASA, and we will be taking those questions for you. With no further ado, Alex Young will start us off.
Thank you, Karen. So hi, I am Alex Young. I'm the Associate Director for Science in the Heliophysics Science Division at NASA Goddard, and I'm also a solar astrophysicist. And what I want to talk about today are the fundamental science questions that are driving the Parker Solar Probe mission. So if you could put up the first video, please. So the sun is incredibly dynamic. It's always changing, always in motion. It goes through periods of incredible violence and relatively calm periods, but it's incredibly dynamic star. And like other stars, the sun has an ocean of particles and radiation which are flowing out of it, and they're dominated by its magnetic field. And this constant flow of energy and material, something we call the solar wind, permeates the entire solar system. And the extent of the solar wind in the sun is from the sun all the way to the edge of what we define as the solar system. And the space in between is created an environment that's driven by this solar wind. So one of the things that NASA is very concerned about is understanding this environment, to characterize this environment, because this is our regime. This is where we live. In fact, we have technology, we have people in space, and we have to understand and characterize this place that we're traveling through. The solar wind is something that is one of the fundamental things we want to understand, one of the fundamental questions that we're trying to address here today. And this is, why is the solar wind so fast? The solar wind goes from sort of a steady breeze to an actual supersonic flow from the corona, going to millions of miles an hour. So why does this happen? What is going on here? Now, in 1958, Eugene Parker wrote a seminal paper describing why the solar wind does this, explaining the solar wind and explaining why it goes from a subsonic to a supersonic flow. And this research is fundamental to how we understand the atmospheres of stars, and in particular how we understand the atmosphere of our sun. But we don't just have the wind, the sun also has storms. In particular, the sun can blast out these huge blobs of material, billions of tons of solar atmosphere threaded with solar magnetic field, traveling away from the sun at millions of miles an hour. And so we want to understand why this happens in the corona and take this data to further improve our models so that we can better predict this, what we call space weather. And this space weather has direct influence, not always positive, on our technology in space, our spacecraft, can disrupt our communications. It creates a hazardous environment for astronauts. And in the most extreme case of these space weather events, it can actually affect our power grids here on the Earth. So it's of fundamental importance for us to be able to predict the space weather much like we predict weather here on Earth, terrestrial weather. So those are sort of two fundamental questions: the speed of the solar wind, this space weather, explosive space weather storms. But the last question that we're interested in understanding is the corona itself. It's a very strange, unfamiliar environment for us. We're used to the idea that if I am standing next to a campfire and I walk away from it, it gets cooler. But this is not what happens on the sun. As we go from the surface of the sun, which is 10,000 degrees, and quickly move up into the corona, we find ourselves quickly at millions of degrees. So this is a fundamental question that drives not only how this star works, our sun, but actually all the stars in the universe. How does these atmosphere work? And so these are sort of the three fundamental questions we want to address here today: the speed of the solar wind, this eruptive phenomena, solar storms, and how is the corona heated? Thank you.
Thank you so much, Alex. Now that we have some sense of why NASA wants to study the sun and study the space environment, we are going to move on to talking to Nicky Fox. She is the project scientist for Parker Solar Probe, which is scheduled to launch on August 6th, right here from Kennedy.
Thank you very much, Karen. Yes, as Karen said, I have the great honor of being the project scientist for this amazing mission. Alex just did a lovely job of really highlighting why we need this mission so much and why we're so excited as a science community to be finally flying it. These questions: why is the corona about 300 times hotter than the surface of the sun? Why does this coronal atmosphere, that atmosphere that you probably all saw last year during the total solar eclipse, why is this suddenly accelerated and moving away? In 1958, as Alex noted, a seminal paper written by Dr. Gene Parker from the University of Chicago predicted all of this stuff. It is no coincidence that the mission we are talking about today is Parker Solar Probe. Last year, we renamed the mission for Gene Parker. It was the first time that NASA has ever named a mission after somebody during their own lifetime. And we're extremely excited not only to bear his name, but also we're looking forward and anticipating him joining us here at Kennedy Space Center in a couple of weeks when we launch this mission. And so the science is groundbreaking, it's compelling, it's confused scientists and puzzled us for decades and decades and decades. We're now going to fly this mission. So let's sort of dive into how we're going to do it. So we will launch, as Karen just said, August 6th from Slick 37 on a very beautiful United Launch Alliance Delta IV Heavy. If you have a chance to go see it, it is a beast of a rocket. On top of that, we actually have a final stage, a third stage that's going to kick us even more so when we get out into space. We need to go so fast because we have to lose the influence of the Earth. The Earth is traveling around the sun very happily. We do not want to travel around with the Earth. We want to be able to go in towards the sun and really fly through that corona. So we will launch just 6 weeks after our launch. We will encounter the planet Venus for the first time, as this animation will show. Venus is very important to us. 6 weeks, it's a very busy time for us, but we actually use Venus to do gravity assists. Now, not like those other missions you've heard about that, take energy from the planet to speed up. We actually generously give energy to Venus, and we use Venus to slow us down just a little bit, really to focus our orbit, almost like doing a little handbrake turn and focusing us in towards the sun. We will do 24 sort of petal orbits, as this animation shows. Coming very close to the sun on one side, going out around the orbit of Venus on the other. I mentioned Venus is very important for us. We will encounter Venus another 6 times during our 7-year mission, allowing us to walk closer and closer into the sun until at our closest approach, we are just 3.83 million miles above the sun's surface. And a lot of people don't think that sounds particularly close, but if I put the sun and the Earth in the end zones on a football field, Parker Solar Probe will be on the 4-yard line in the red zone knocking on the door for a touchdown. So we're very close. There is also a model in the press office here that shows exactly where Solar Probe will be sitting relative to those coronal field lines. Very, very close. Also very fast. At our closest approach, we will be traveling at 430,000 miles an hour, or about 118 miles a second. So fastest human-made object also. We need to go to the corona because we have done so much science by looking at the spacecraft, at the star. We've looked at it in every single different way you can imagine, every wavelength. We've traveled in beyond the orbit of Mercury even, but we need to get into this action region, into the region where all of these mysteries are really occurring. And that's why we are doing this incredibly daring journey, if you like, through the corona 24 times. We are very happy that we are well protected. We have a full suite of instruments to make the measurements that are so key and important for us to be able to close the science that Alex has talked about. So we have instruments that measure all of the magnetic and electric fields. They're looking for plasma waves, the very high energy particles, and we also have a white light imager that is taking pictures basically of what we're about to plow through. And so we have a full suite of instruments. We are nicely protected by our heat shield. Karen already alluded to, and Betsy's going to give you a demonstration in a minute. But if we look at this nice animation, you'll see Parker Solar Probe with the heat shield facing towards the sun and protecting the bulk of the spacecraft from the solar wind. Most of the instruments sit on the main body of the spacecraft. You can see it, the sort of silver structure at the back there, and they are well in the shadow provided by that amazing heat shield. There are a couple of instruments that brave the solar atmosphere. I think of them as very brave little instruments. They peep out around the side, and they have to be in that full environment. And you're going to see a video in a minute from Patrick Hill actually showing you all these things on the spacecraft, so you'll get a good feeling for where these instruments are. Not only do we have a heat shield, we use solar panels, solar power, to really run our mission. That may sound like a no-brainer. Hey, Nicky, you're going to the sun. Big deal. But of course, solar cells need to stay cool. They don't like to overheat, and if they do, they don't work. And so we had to find a way of being able to cool our panels as we are making these cuts through the corona. One final thing for the big technology is she is the most independent. I like to think of her as an independent spacecraft, but she's highly, highly autonomous. She has to look after herself when she's in this coronal region. There is no person in the loop. She is fully capable of figuring out if there's an anomaly, how to rectify it. It takes light 8 minutes to get from the sun to the earth. We don't have time for her to send a signal, somebody to think about it and send it back. She has to be able to look after herself. And so these are kind of the big technology leaps that we've had to make. That is why we've had to wait 60 years for this mission. And so I'm happy to say that after waiting this long, we are now at the finish line and ready to launch our mission, join all the other wonderful missions that NASA has. Looking at the sun, we're going to be providing that last piece of the puzzle. And so in just a few weeks, we will go and touch the sun.
Fantastic. Thank you, Nicky, so much. We had a chance here to talk about the science, a little bit about what Parker Solar Probe is going to be doing. We next want to tell you all about the spacecraft itself, the kind of things that are on there, and how it will be working. To do that, we have Patrick Hill on a video. He is the Deputy Project Manager for Parker Solar Probe from APL, and you can roll that video. Thank you.
Hi, I'm Patrick Hill, Deputy Project Manager for NASA's Parker Solar Probe. I'd like to take you on a tour of the pioneering spacecraft designed, built, and soon to be operated by the Johns Hopkins Applied Physics Laboratory. In just a couple of weeks, a Delta IV Heavy launch vehicle will rocket Parker Solar Probe out of Earth's atmosphere and begin its long-awaited mission to touch the sun. There are three main technologies on Parker Solar Probe that make this mission possible. They all play an integral part in keeping the spacecraft and instruments safe, healthy, and operating at peak performance. The Thermal Protection System, or TPS, is an essential technology that enables Parker Solar Probe to get so close to the sun. During closest approach, the sun-facing side of the TPS will see temperatures around 2,500 degrees Fahrenheit. Meanwhile, the spacecraft itself will be closer to room temperature, around 85 degrees Fahrenheit. Everything hides behind the shadow or umbra of the TPS, except for a few brave instruments: the field's electrical wave antennas and the Sweep Solar Probe Cup, both of which have their own heat shields. Like many spacecraft, Parker Solar Probe is powered by solar arrays. There are two on each side of the spacecraft, currently hidden beneath their protective covers. What's different about our solar arrays is they must operate within the final 5% of the distance between the Earth and the Sun. That's too much energy for conventionally designed solar-powered systems. The first thing we do is use the actuator motors to move the solar arrays behind the umbra of the TPS, such that only the leading edges are exposed to the sun. That small amount of illuminated surface produces enough energy to power the spacecraft and all of the instruments. The spacecraft uses an innovative cooling system that circulates water throughout both arrays. The heated water is then transported to these large radiators hidden behind the TPS, which then radiates that heat out to deep space. Parker Solar Probe is the first spacecraft to use an actively water-cooled solar array system. During solar encounters, the sun itself blocks Parker Solar Probe from receiving commands from the Earth, and it must rely on its own autonomous systems to keep the spacecraft and science instruments safe. We've placed solar limb sensors all over the spacecraft to determine when it's receiving too much sunlight. Autonomy then determines how best to position the spacecraft by sending commands to the reaction wheels, which adjust the probe's position in space. Parker Solar Probe is one of the most autonomous spacecraft ever designed. Parker Solar Probe culminates the work of tens of thousands of people at NASA, APL, and our partners all over the country and all over the world. It's been an honor to work with such a deeply dedicated and knowledgeable team of scientists, engineers, and technicians. I can only wonder what we'll discover along our mission to touch the sun.
All right, we will be answering questions in just a moment. Remember, if you are on social media, you can use hashtag #AskNASA for that. We have one more demonstration in this room. Before that, we have Betsy Congdon to come up. She is the lead for the thermal protection system, this heat shield right here.
Hi, I am Betsy Congdon. I work at the Johns Hopkins University Applied Physics Lab, and I am the lead engineer for the heat shield, also referred to as the thermal protection system, or TPS, for Parker Solar Probe. And I'm going to do a little demonstration here of the heat shield material. What I have next to me is a slice of the heat shield that you saw. We lovingly refer to the heat shield as our 8-foot frisbee because it is about 8 feet in diameter, 4.5 inches thick, but only about 160 pounds. And Nicky talked about how fast we had to go, and everything on this spacecraft really had to be lightweighted in order to achieve those mission objectives. So I'm going to get started here, getting this hot.
I'm going to bring up a volunteer from the audience. I'm going to come on up. Somebody who will be able to help with the demonstration. You can tell us who you are, and you can stand over here.
All right, I'm Mary Liz Bender with the Planetary Society, and I'm very ready.
And I'll put you right over there behind. Great. Oh, do we need a match? Oh, we got it.
Okay, so as you saw in the video, the heat shield itself does have a white coating, and that white coating was specially designed for Parker Solar Probe. White is better at reflecting heat than black. It's a lot like being in a white car on a hot day as opposed to a black car on a hot day. It's just better. The heat shield itself is a sandwich panel. Sandwich panels are used commonly in situations where you need a lot of structure, but needs to be very lightweight. Aircraft are often made of sandwich panels, and actually Parker Solar Probe, the main bus, is an aluminum honeycomb sandwich panel. In this case, it's a superheated sandwich panel. So we have two outer face sheets. They're both carbon-carbon, which is a lot like the graphite epoxy that you would find in your golf clubs. It's just been superheated. In the inside, there's carbon foam, And the carbon foam is actually about 97% air, and it's just there to take that heat. It's a very efficient system, both structurally and thermally. As mentioned, the front surface is at about 2,500 degrees Fahrenheit at closest approach. The back surface, that back surface of the 4.5 inches, is about 600 degrees Fahrenheit, and the bus is sitting at about 85 degrees Fahrenheit. So it's an impressive thermal system altogether. So I'm starting to get this pretty hot. I can feel it. Yeah, the propane. So it's starting to get a little hot, a little red on the front surface. You want to take a touch of the back surface? See? I want you to touch the back surface, yes.
I'm going to actually touch it.
How does it feel?
Lukewarm, not even,
Normal room temperature. As you can see, it's glowing red hot on the front surface. You definitely don't want to touch the front surface of this. Okay, so I think I will turn this off. Just a little demonstration. Still cool? Still good?
Perfect.
Awesome. Thank you for demoing. So obviously this wasn't quite as hot as we get at the sun, but it's just a little demonstration of how well this functions. And Karen.
All right, you can stay up here with me because we're going to answer questions now. Maybe not with the blowtorch.
Yeah,
Drop your blowtorch. Great. We're bringing Alex Young back up, Nicky Fox. We're going to start with questions in the room. Already got some hands, so here we go.
Stephen Young with Astronomy Now and Spaceflight Now. As a science team, you must be pretty excited you're getting close to launch now. But I would imagine there are some pre-launch nerves as well. You've had some sensor problems and software issues that you're still working on. Could you give us an update on what is left to do to assure that everything's going to work as you intend when you launch?
Sure. I'm happy to say that Parker Solar Probe is inside the fairing. She is totally in her flight configuration. We have done all the work, all the checks. She finally looks exactly like I expected her to look from all those PowerPoint presentations I saw 10 years ago. All the blankets are off. The flight blankets are on. All the protective covers are off. We did have a we were lucky enough to find out we had a issue with our temperature sensors. We had a great team that came in and put a totally redundant system in, so that is all good to go. All our flight software loads have been made, and she is buttoned up, looking beautiful, and totally ready to take her flight.
Yes, please.
Hello, Marcia Dunn, Associated Press. Science questions for either or both of you. On each orbit, generally speaking, how much time will Parker be in the corona? And, you know, I read about the corona being millions of degrees hot. How is it that you're only experiencing 2,500 degrees?
That is a great question. I love that question. Yeah. So first of all, the prime science gathering, I mean, the instruments, the goal is to have them on us all the time, but the actual sort of prime science gathering for us is about 11 days. And we say it's from 0.25 AU, so a quarter of the distance from the sun to the Earth, around and then back out again. That's kind of our encounter period. And so, you know, that's where we really consider the outer part of the corona and then coming right in and sweeping through. Yes, the plasma is at a few million degrees. And yet I said the temperature, and Betsy will kill me if I say only 2,500 degrees, because I'm not allowed to say that. But if you think of putting your oven on, and you set it at 400 degrees, and you can put your hand inside your oven and you won't get burned unless you actually touch a surface. And it really is the same. The corona is very tenuous plasma. It is not a hugely dense area. I mean, you need this entire sun to be blocked out by the moon to even see it. So it's not as dense. And so if you think about the amount of particles that actually are striking the heat shield and depositing that heat in, the whole thing gets heated up to 2,500 degrees Fahrenheit. But again, you know, like I would just say, don't touch the oven surface, don't touch the 3 million degree plasma. But that's why it gets to 2,500 degrees.
Days more or less
each orbit.
Each
yes.
orbit.
Yes.
Okay, thanks.
More questions from the room? Yes, please, right there.
Thanks. Irene Klotz with Aviation Week. What's the nominal mission duration and the cost of the mission?
So the nominal mission duration is 7 years, and that is the 24 orbits, a little bit on the end to bring down our final data. And the official NASA cost for the mission is $1.5 billion. It includes the launch vehicle.
What happens at the end of the mission? What happens with the spacecraft?
So at the end of the mission, our last petal orbit, where we're in that final configuration, we are inside, pretty much inside the orbit of Venus at that point, so there's no more VGAs possible. But that last orbit is completely stable, and so we can stay in that orbit while we have the fuel to be able to maintain our attitude. Once we run out of fuel, the spacecraft will start to turn, and because they will no longer be able to keep orienting that heat shield. At that point, parts of the body that are not designed to see the full solar environment will then see it. The spacecraft will start to break apart. It will break apart into large pieces, and then it will get gradually smaller. And so I romantically like to think that she will become part of the corona and orbit the sun forever.
Thanks. And then I have one science question. The last time, Alex, I think we spoke was before the eclipse last year, and just was wondering, I know that was purely not for, science was made of it. It wasn't really intended for any science, but was there anything that came out of the studies that were done that sort of changed thinking or has any impacts at all in the thinking of this mission?
There's actually a lot of science. I mean, I could go on. So there's just the science of looking at the corona. Some of those results are still being processed because, in all honesty, there's so much data that they got during the eclipse from ground-based and aircraft that they're still processing a lot of that. So we're hoping to see some of those results probably actually in the next month or so. One of the first most fundamental things actually I think was something Nicky brought up earlier talking to the audience. The predictions from predictive science of what the corona would look like were amazing. The quality, the structure they saw, and what we actually observed were literally spot on. So that was the first science really that came from the eclipse. So that was fantastic. The rest of the science actually has a lot to do with the atmosphere. There's a lot of really interesting studies that were done of the atmosphere, the part that we live in here on Earth. When I say the atmosphere, Earth's atmosphere, but also the ionosphere. The science that was done to study the ionosphere was incredibly rich because it was across the U.S. and we had such broad coverage, radio coverage, in terms of the various types of radio arrays around the country in this particular part of the world, gave us a detailed understanding of the ionosphere that we've never had. And we actually showed results from papers that were written 40, 50 years ago that were finally confirmed during that eclipse. So there's a lot of incredibly rich science, and it will continue to come out over the next couple of years.
We'll take one more question from the room now, some phone, and then we'll come back here.
Hi, Kent Kramer, Space Up Close, Rocket STEM. My question is specifically about touching the sun. I think it's the ESIS instrument.
Yes.
Can you describe how will that collect and analyze the particles?
Certainly. So there are, it is a complete suite that we're using to look at the various different aspects. The ESIS suite that you particularly picked on, they are looking at the very high energy particles. So the particles that are associated with shocks, with flares, with the coronal mass ejections that Alex showed all those beautiful movies. There is also the SWEEP suite, which is looking at the sort of the bulk solar wind. And so, if you think of it as kind of the river flowing downstream, SWEEP has three different sensors that are looking at the stuff that's flowing all the time and sort of picking up all the little features that are in that continual flowing atmosphere away from the sun. And ESIS is kind of almost like looking at the motorboat that goes down the stream that is going much faster and much more energetically, but isn't always there. It's associated with these transients. The fields suite is looking at all the magnetic, electric fields and the plasma waves that kind of reside in, we think the magnetic field is the number one thing that's really causing these mysteries in the corona. And so highly important to be able to do that. the waves are floating around as the particles are changing, and then of course our white light imager that is taking those images of what the spacecraft is about to plow through. And so together, that is how we will answer all of these questions.
So there's like a porthole that collects the particles and.
There are apertures, yes, that the particles can enter through, and then they'll strike onto either charge capacitors, or there's different. We've got electrostatic analyzers, and yes, and the solar probe cup. Obviously, it's striking the grids and looking for the voltage signals.
Thank you.
Great. We're going to go to the phones now with Stephen Clark with Spaceflight Now. You can ask your question.
Hi. Thanks for taking my questions, if I may. First, to follow up on one of my colleagues' questions about the temperature sensors on the spacecraft. I think Dr. Fox mentioned some redundant system was installed. Can you expand on that? Did you install new sensors in the clean room, and what was the actual original issue or concern with that? And secondly, I'm wondering just some information on the timeline of the mission. I know you're first this year. Can you talk about what kind of science you're going to get early on, and a few months after launch, and then how the science may improve as you dip deeper into the corona over the next 7 years? Thank you.
Yes, sure. So yes, the temperature sensors, we did find an issue. We had a number of them that had failed during testing, and we were able to put a new system that basically they're located in the same sort of real estate next to the original ones, and as anything fails, it rolls over onto the new system. And so we've done a full testing of the second system, and we're very confident. And we've done many good tests to show that both of those systems are now working well. And any issue we roll over to the new system. So that was a good catch, good find, and fantastic effort by the team to rectify that and keep us on our march towards launch. You asked about the science. So we will actually, in our very first flyby of the corona, we get to just it's a little more than 15 million miles away from the sun's surface. So we're still 3 times closer than anything has been before. And so we're already in a region of very, very interesting coronal area. In fact, one of the key things about our early orbits is we're actually just at this sort of sweet spot where the plasma that we're flying in through a flux tube, and we stay in the same flux tube. And then as we're rotating around the sun is rotating at the same time, the same speed. So, if you think of it in that frame, the spacecraft is staying over the same area of the sun for many, many days, allowing us to do some really incredible science on our very first flyby.
And I wanted to add something, just because the eclipse was mentioned. We actually have an incredible opportunity, so that while the observation times are not a one-to-one correspondence, Parker will be looking at the corona and flying through the corona near the time of 3 total solar eclipses, including the 2024 total solar eclipse in the United States. So we will be measuring the corona, studying the corona up close and personal, and we'll be looking at it with incredible detail here on the ground during total solar eclipses. And that is a first.
Yeah, that is fantastic. Yeah.
We have another question from the phone. This is Jim Siegel with Spaceflight Insider.
I have a question relative to one of you mentioned earlier about one of the hazards of solar winds and solar climate is how it affects the power grids here on Earth. And so I'm interested in how frequently that occurs, if at all. Have there been any, for example, big examples of that in the recent past? And I'm also wondering, given maybe our more reliance increasingly on the solar grid, do we expect that without this information from this mission, our solar grids are going to be more vulnerable in the future because of our greater reliance on grids, power grids? So that's it. Thank you.
All right, I'll jump in first and then let Alex jump into. So yes, we are as a society, sorry, we become more and more reliant on technology. And so what in 1859, when we had the Carrington event and the telegraph system went down for a few days, that was terrible at the time, but you try telling your kids now they're going to lose their internet for 4 days and national panic will ensue. And so we have a very, very, very different way of the way we live now. And so yes, we are totally reliant on power grids, and yes, a big aurora, beautiful aurora is like having a big current flowing through the sky, and currents have to find somewhere to close. If the ground underneath you is non-conducting, they will look for something long and straight and conducting that they can flow through, like a power grid. In 1989, we had the famous Hydro-Quebec power failure, it was a catastrophic failure of the entire grid, and 6 million people were left without power for many days. And so, yes, we do have these things. We are right now in a period of somewhat quiet solar conditions. Not that we haven't had recent events, but we are in somewhat more of a quiet. The big thing for Parker Solar Probe is, if you think of the sun and the earth as a system, we understand all of the pieces, but we don't have the physics that drives the solar wind. And so by doing this mission, we're going to go make those measurements, understand what we should be putting into those predictive models. And that is how Parker Solar Probe will help protect society from the vagaries of the sun.
Yeah, so Nicky covered the main point, but it really gets down to the fundamental physics. A great deal of what we can do now in terms of space weather prediction is statistical. We can't do much better than, saying there's an 80% chance of something. That's just based on past conditions. Just like when we do prediction of the rain, all we can say is the conditions were like this in the past, therefore 8 out of 10 times it rained, therefore is 80% chance it rain. That's not really getting to the fundamental physics of why. And so now that we're going there, we're going to be measuring the fundamental processes that are happening at the source. This is going to provide unique input into models that will lead us to the point of actually truly being able to maybe make real predictions, not just on a statistical basis, but on a physics basis, and that's the key.
Thank you. We're going to take 2 social media questions, and then we will come back to the room. I know there were some more questions here. Please.
All right. Jamie on Twitter would like to know, was the Delta IV Heavy rocket picked to launch the probe for any special reason?
Yes, the Delta IV Heavy was picked because we need to have an incredible lift, a real sort of big Delta V, a real big kick off the planet. And so not only do we need all of the awesome power of the Delta IV Heavy, but I mentioned we also have the third stage, which of course fires when we're already outside the atmosphere and gives us more than half of our Delta V, actually. But yes, the Delta IV Heavy took a lot of strain off that third stage by providing it that extra power. And so we are using every single drop of the Delta IV Heavy. As Betsy mentioned, we have to be as light as possible just so we can lose the momentum of the Earth and be able to go into the sun.
Thank you.
Christopher from Facebook, will there be any science gathered during Venus flybys?
The science during Venus flybys, for most of our flybys, that's actually during our prime downlink of our science data from the corona. As Patrick mentioned in his video, a lot of the times the sun is between us and the satellite, and so it's very hard for us to be able to see and close that link. And so whenever the spacecraft comes close to the Earth, we pull down all that data. Most of those Venus flybys are during that period, and our instruments are switched off so that we can put all the power to getting our coronal data down. There is I think it's the 6th VGA where we will have the instruments on. We're not downlinking data, and so we'll be interested to see what measurements we can make as we whip past Venus on that one.
Great. Let me bring it back to the room. Some questions here. Yes, sir.
Hi, Emery Kelly with Florida Today. As I understand it, it's highly unlikely, but as I understand it, the launch window for this mission closes August 19th, August 20th. Worst case scenario, what happens if that happens? And second question, obviously there are a lot of moving parts to this mission. in terms of anomalies, what are you possibly expecting? Thanks.
Sure, I'll take the launch window one. August 19th, you are correct, is the date. There's always the chance we can push for a couple extra days, but that is our window. And of course, the whole point is we have to get to Venus at the right time, so would have to adjust for a different launch time for that planetary necessity.
As far as anomalies, I mean, in the beginning, it's pretty standard spacecraft anomalies. If something doesn't work exactly as you think it does, it's really hard to predict. I mean, we've operated a lot of spacecraft, we've launched a lot of spacecraft. We know the type of things that can happen, and we're ready to watch for it. It's really no different to any other mission for making sure that you've got all your fault management system and everything is all buttoned up and ready to go.
All right, another question here.
Stephen Young with Astronomy Now and Spaceflight Now. For Nicky, the wide angle camera that you have on board, what will that see, and what sort of wavelengths are you looking in? And will we see those things, and will they be blockbuster images that we'll all be very impressed by?
Well, I'm going to love them. So it's a white light imager. And so it will look very similar to the corona that you saw during an eclipse, only yet even more tenuous as it moves away. And so there are some very nice images from the stereo spacecraft. Craig DeForest, a researcher at Southwest Research, has just published a really nice paper looking at some of the structures that he got from these stereo images. And so it's like it looks like maybe dust flowing fast, but to us we can see structures in that sort of, you can see like little particles. And so it's important for us because, these instruments, this is the first time we've gone into this region of the unknown. We are traveling at roughly half the solar wind speed. I mean, I mentioned 430,000 miles an hour, and the solar wind's traveling at roughly 1 million miles an hour. So sometimes we're traveling in the same direction, and so all the features will get kind of smeared out. And then other times we're ramming into it, and everything is going to get really sort of compressed. And so having that imager to be able to show us, oh yes, that's it. Look, it's a flux rope, and it's a flux rope, yes. And so it's really, really, because a flux rope's going to look very different when it's this big to when it's this big, depending which way you're traveling. And so being able to see what kind of structures, what transients, what is flowing towards us is really important. It is not going to look like an SEO image, nor indeed my dress. It's not going to look like that. We are actually we are blocking. We use baffling to make sure it doesn't see the sun. So it's more like a traditional coronagraph, but tuned to see that more tenuous atmosphere that the spacecraft will see on for most of its orbit. But I would say spectacular coronal images, but I'm a little biased. So.
Great, we're going to go to a phone question now. Space.com is on the line. You can ask your question.
Hi, thanks so much for taking the time. I wanted to talk a little more about the autonomous decision-making abilities of the spacecraft. Could you explain a little more what that process will entail in addition to regulating the thermal input of the satellite, but what other factors that will play into?
Yeah, I mean, there's a really simple example, which is there are 7 sun sensors located around various parts of the spacecraft, and none of those sun sensors should ever see the sun. The moment one of them does, the spacecraft knows, hey, this one, I've started to tilt in this particular way. I need to fire a thruster. I need to, make the momentum wheel go faster. And so all those things are sort of programmed, pre-programmed, and unbelievably tested, as you can imagine, to make sure that so that is sort of one nice example of the autonomy. There's also things like making sure we know how much power is coming off the solar panels. If it increases over a certain level, then tuck those solar panels in. The video was a nice demonstration, and Patrick also talked about the fact that the solar cells are sort of articulated like on shoulder joints, and so we can tuck them in until it's just like your fingertips are sticking out. So if we suddenly see too much power, the spacecraft can adjust those solar panels. So there are a couple of examples.
We have another question on the phone from NASA Spaceflight. Go ahead.
Yes, thanks for doing this. A follow-up with the autonomy question and then a follow-up after that. So for the autonomy portion, am I correct that there are still elements that if something goes wrong during these coronal deep dives, that the probe will still enter safe mode to protect itself at all costs until it can swing around and a human would be in the loop? And then a follow-up to that is, can you talk about some of the space-based applications for the technology of the sun shield and the radiation shielding for other satellites and some of the more practical applications that the technology on Parker Solar is demonstrating?
Okay, so I'll take the first part and say that, yes, we also, in addition to this sort of super duper autonomy, we also have the more standard, if something happens, you safe and protect until, somebody can get in the loop and look at that subsystem. So for the instruments, for example, if they saw a problem, they would take down a high voltage, or they would, do something to protect themselves. So they will survive their journey through the corona, and then we could do analysis on it outside, which is like pretty much any mission that we fly. The addition here is all this ability to keep the attitude system absolutely perfect. And then Betsy, I'll let you take your baby heat shield and talk about that.
So the heat shield technology itself, while different than any heat shield that's been built before, is built on some of the materials and technologies that have been used before. The lead engine of the space shuttle, or the lead edges of the space shuttle, actually are a heritage of then some of the materials you see here. And some of the development that we did has a good understanding of how we might do heat shields in the future in lighter weight ways, more efficient ways. Additionally, the autonomy system, which, like Nicky mentioned, is most autonomous spacecraft that's ever been built, learned how to do that, how to do fault management, and that will flow through to future missions and how we actually run spacecraft in the future and kind of change our capabilities.
Thank you. We have a couple more questions in the room, but we're slowly running out of time. I want to give the AP a chance, and we'll do one social media. And if we don't have a chance to answer everyone in the room, there will be some availability afterwards to talk here.
An AP with two quick questions. It's sort of an odd-shaped shield. How many sides is it? Is it really an octagon or something else? And then if I'm looking at last summer's total eclipse, and I'm looking at the little wisps of the corona, how deep into that picture will you be?
All right, so let me take that one because that's really easy. Do me a favor. When you leave this building, go into the bullpen, and in there you will see a model that was made, as Alex noted, the predictive science who really predicted what the coronal field would look like. In there you can see a scale model, sun in the middle, all of the field lines draped out, and Parker Solar Probe sitting right there. So it is 4% of the distance. I have a great graphic I can show you on my computer afterwards. But the long streamers, the very long ones, Parker Solar Probe is right on those streamers. Not the super close, sort of the more halo, but the long helmet streamers, Parker Solar Probe is well on those. But do take a look at the model on your way out.
And I'll let you finish, but I'll just add, and when you are observing, hopefully the eclipse, really, really good conditions, you will be looking at the edge of it. So it's something you can physically see from the ground.
Yes.
The edge of your field of view on a good observation time, you will see where Parker is.
Yeah.
And the shape. So the shape is very odd. We were talking about the mass being a critical thing on this mission, so it is perfectly designed to cover what it needs to cover. It's actually not even, it's hard to see with your own eye, but it's actually not even symmetric, and it's not an octagon. It's got two rounded edges with some tangents, and then there are basically 6 flat surfaces, 2 very long flat surfaces, which are giving our knife edges, as we call them, for the solar rays. Nicky was talking about having a very precise, and Patrick did as well. We use those to very precisely control how much energy is making it into the solar rays. So that's why you have those long flat edges. And then the 4 kind of shorter flat edges are actually for the solar limb sensors that we were talking about and how we actually can go understand when something is being illuminated. So every surface on that shield is designed to either protect or perfectly enable something below it.
Great. Social media next.
Yes. Dana from Facebook asks, was the project timed to coincide with any specific part of the solar cycle?
It was not specifically targeted, but golly, we're happy where we are. So I would say it's serendipity that we are launching right before solar minimum. Solar cycle 11 years, we're a 7-year mission, which means we will go from solar minimum and crest solar maximum, and then, hopefully be able to go even a couple of years beyond that within an extended mission. And so it's a happy accident. We're delighted. It was not planned that. I wish I could say yes, we planned it that well, but it's really, really fantastic for us exactly where we are.
To cover more than half a solar cycle is incredibly powerful for the science.
Yes, and to do the minimum to the maximum, not halfway up across maximum and down, is really fantastic for us, yes.
All right. We'll do one more question in the room, and as I say, we will have people available to talk afterwards. There are a whole bunch I'm going to give you since you haven't asked one yet.
Thanks so much. Joey Roulette here with Reuters News. Would you say this is perhaps the most ambitious project under the Living with the Star program? And I don't know if this was mentioned before, but how soon will we get the first pings of data back from the probe?
Honestly, I would say every mission that NASA does is ambitious. It's what we do. We push the boundaries, we push technology, we do everything else. Certainly to send number one, to send a probe where you haven't been before is ambitious. To send it into such brutal conditions is highly ambitious. SDO and Van Allen probes are doing fantastic things, and I would hate to say that they were not ambitious. SDO had an incredible challenge of bringing down terabytes of data every day and had to figure out how to do that. The radiation belt storm probes, sorry, I'm old school, the Van Allen probes, it rolls off the tongue too easily for me. The Van Allen probes live and work in regions that most spacecraft try and avoid. And so I think all of them are doing incredible cutting edge science. They've all had their own challenges. The solar probe is very much at home in a group of challenging missions. And your first peeps of data, we should get our first data down early-ish December. Yeah.
Great. That is all the time we have for your questions right now. We are going to remind everybody you can watch the launch. It is on the morning of August 6th. The window opens at 4:08 a.m., nice and early in the morning. You can watch that at nasa.gov/live. You can stay in the conversation using @NASASun, and we look forward to continuing to answer your questions as needed. We are going to end our TV broadcast with a message from our Associate Administrator in the Science Mission Directorate. This is Thomas Serbukin, who has recorded a message for us from NASA headquarters. You can roll that.
Hey, I'm Thomas Serbukin, the head of NASA's Science Mission Directorate and a solar physicist. The Parker Solar Probe mission is heading to a region of space never explored before. This is truly a mission for all humankind and will forever change how we view the sun. Parker Solar Probe is the newest addition to NASA's heliophysics fleet. These missions study the vast interconnected stretches from the sun to the space surrounding Earth and other planets to the farthest limit of the solar system, where the sun's constantly flowing streams interact with the galactic environment. Parker's data will improve forecasts of major space weather events that impact life on Earth and satellites and astronauts. It will help provide situational awareness needed for future missions to the Moon, Mars, and beyond. While we have many missions dedicated to studying the sun from afar, we have never, ever had a mission to get this up close and personal. Just think for a moment when you look up and see the stars. They are so far away that with current technology, it will take millions of years to get close enough to study even the nearest one. However, we have a star we can travel to and begin studying in mere months. That's our sun. You're probably thinking, why do we need to touch the sun? Well, by studying our star, we can learn more about all the other stars throughout the galaxy, the universe, and even life's beginnings. This mission has many firsts, including the namesake, Eugene Parker. In fact, this is the first time NASA has named a spacecraft for a living individual. It's a testament to the importance of his work founding the field of science that inspired many important science endeavors, including my own research. Parker Solar Probe will face intense heat and radiation unlike any spacecraft in history. But don't worry, the instruments will operate at room temperature, most of them at least. This is possible with cutting-edge thermal engineering advances that will protect the mission throughout its trailblazing journey. Finally, this year marks NASA's 60th anniversary of research and exploration and has fundamentally transformed our understanding of Earth and the universe we live in. Parker Solar Probe will now join that unprecedented NASA history by helping us answer questions about solar physics that we've puzzled over for more than 6 decades. The investments in this mission will return a better quality of life and create knowledge and drive inspiration that benefits all of humanity. Thank you for joining us today to learn about NASA's Parker Solar Probe, a mission to touch the sun, a mission to touch us all. Go Parker Solar Probe.